Hello everyone, today let's take a look at quantipose number 72, probably demonstrating the coolest property of derangements. And it's honestly kind of more of a calculus problem, but it's just a good thing to know. So basically we want to estimate the probability that a random permutation of 1 to 1,000 is a derangement. And the reason it says estimate and this number is so large right here is that because we're not going to be able to work this out in any feasible amount of time by hand, obviously. That's just because to calculate a derangement, it's just going to be a long series, in this case 1,001 different binomial coefficients that we're going to have to add up and calculate. But we can come up with a really good approximation by considering this limit here, and we can add in some bonus points to see how far our approximation differs from the actual value of p sub 1,000. So let's start out by doing what the hint is telling us. Let's consider this limit as n goes to infinity of p sub n. And p sub n is just the probability that a random permutation of n objects is actually a derangement. And we know how to calculate p sub n. It's just going to be the number of ways to derange n objects, d sub n, over the total number of permutations of n objects, which is n factorial. So how do we actually calculate d sub n? Well, let's just get the formula by looking at a quick example that we've been working with a bunch, which is going to be d5. So for d sub 5, we've been doing this a lot, right? It's going to be equal to 5 factorial, the number of total ways to permute these elements. Now we need to subtract off the cases where the elements are in their correct spot. So let's just fix one element. We have 5 choose 1 ways of doing so, and then we have 4 factorial ways of permuting the others. Then we need to add back on the 5 choose 2, the ways we can fix 2 elements, and the 3 factorial ways of permuting the others. And we know the drill at this point. We just need to subtract off the number of ways to fix 3 points and then permute the others and add back on 5 choose 4 times 1 factorial, which is 1, and subtract off finally 5 choose 5. So this is how we've been doing it for 5 elements, but now let's turn it into a formula when we have n elements. Okay, so obviously I'm going to be taking some type of sum here. Let's just say our iterator is k. Now let's just look at some of the terms in our series. Obviously every term is going to have this binomial coefficient where the top part is the subscript down here, right? The number of elements that we have. So it's going to be n, and on the bottom we're iterating it. We're using our iterator, so it's going to be k. And then in all of our terms, we appear to have this factorial as well, where it's getting decremented each time. So let's start at n, and we're going to subtract off our iterator k. And then obviously it's an alternating series, so we need some type of -1 term raised to the power of our iterator. Now let's just do a quick sanity check. Let's make sure that this actually represents what we're seeing over here. So my first term, when n equals 5, I want it to be 5 factorial. So I want k to start at 0, and that also makes sense because this would make this term 1. So you can see our first term is showing up, and we want it to be positive, so that all works. Now for our second term, k is going to iterate to 1, and then we're going to get 5 minus 1 here, which is going to be 4 factorial, which makes sense. We're going to get 5 choose 1 here, which also appears, and then we're going to get -1 to the power of 1, which is a negative, and that also appears here. So you can keep on iterating and see that this formula makes sense when representing d sub n, right? And when we get to our final term, it's going to be 5 choose 5, so our final number of the iteration is going to be n. Okay, so we have our formula, so let's just get rid of this to make some space. Okay, now I've scrolled down to make a little bit more space, but now let's just expand this binomial term. It is n factorial on k factorial times n minus k factorial. So plugging that back in, you see we get this nice cancellation right here. And we can pull the n factorial out, so this is just going to be equal to n factorial times the summation of k equals 0 to n of -1 to the power of k on k factorial. So this is what d sub n looks like right here. So if we plug it back into this over here where we have p sub n, that's the probability of derangement. Well, you can see now I've just plugged the d sub n term from down here up in here, and we can see that the n factorial now is going to cancel. So p sub n is just going to be equal to this. So now let's come back up one more. Now let's take the limit of this p sub n. So this is just what it looks like when we plug in p sub n. And you might notice that this looks very familiar to something that you know from calculus, right? And I'll probably make a series later on explaining more of this calculus stuff, but basically what you should realize is that this looks a lot like the Taylor series expansion of e to the x. So you'll notice that if we plug in -1, if we expand the Taylor series for e to the x around -1, we get exactly this formula right here. So therefore, we know that this is going to be equal to e to the -1, which is also known as 1 over e. And this is the really cool thing about derangements. This is basically the property that we are trying to find. The probability of derangements as n gets very large just approaches 1 over e, and it approaches 1 over e very fast. So if we had to estimate, right, that's what the original question was asking, p of 1,000, well, we could just say it's basically equal to 1 over e. So we basically found that P sub 1000 is approximately 1 on E, but now we need to do the bonus points. How good exactly is this estimate? So to find that, let's just take the difference between our estimated value, which was 1 over E, and let's just subtract off the actual value, P sub 1000. And this right here will give us our remainder. So our estimate 1 over E, this is the Taylor series expansion of it, and basically P sub 1000 was equal to this, which is just the first 1,000 terms of this. So when we subtract off the first 1,000 terms, we're just left with the next 1001 to infinity terms. And it's also a well-known fact with alternating series is that we can actually bound this right here. That's just because the next term in this series is going to be -1 to the 1001 over 1001 factorial. And it's an alternating series with decreasing terms, so we know that the magnitude of this next term right here is going to be greater than the rest of all the other terms. Right, all the terms from 1002 up to infinity, this will be greater than it. And because it's an alternating series, if we take our true value right here, our alternating series will be approximating it like this. It'll get smaller every single time, and it'll kind of approach the true value while going up and down. So all that just to say that the magnitude of our remainder here, right, the difference between our expected and our actual value is going to be basically less than the magnitude of 1 on 1001 factorial. Sorry if the explanation was a little convoluted, that's more calculus, and I'll probably make a calculus series again. But basically, how small actually is this number? Well, it turns out that it's actually less than 10 to the power of -2,569. You can compute this just by taking log base 10 of this, essentially using a computer. And obviously, this is an insanely tiny number. There's only 10 to the 80 atoms in the universe, right? So this is accuracy basically out to 2,500 decimal places. And this is so precise that there's no possible real-world application of anything that requires this level of precision, and there never will be. So you could literally say that P sub 1000 is actually equal to 1 over E.